So today's experiment is an introduction to statistics and data analysis, and it's something that we're going to be applying multiple times throughout the course to get statistically significant information from our experiments and be able to compare them quantitatively to some theoretical prediction. So you can read in your lab manual about the different types of error and about accuracy and precision. You're probably familiar with a lot of that. What you might not be familiar with is the concept of a Gaussian probability distribution. So it's just a type of function that we're going to use to represent a distribution of probabilities. And the total area under that curve, under the function, is going to be 1, representing a 100% chance that some measurement happens. And we're interested in how those possible measurement values are distributed, though. So the Gaussian is always going to peak at the mean value of the data set, and it's going to have a width that is related to the standard deviation, which quantifies the spread of the data set. More specifically, the width of the Gaussian is related to the error on the mean, which is the standard deviation divided by the square root of the number of trials. So we can get a more narrow, a more precise Gaussian distribution by increasing the number of trials. And you want to think about, increasing the number of trials is going to help our precision, but not necessarily our accuracy. So the nice thing about a Gaussian is, because it's a nice well-defined function that fits our data set, it has a well-defined area under the curve at each distance away from the mean. So if we move one error of the mean away from the peak of the distribution, away from the mean, then we're encompassing 68% of the total area under the curve. In other words, 68% of all of the outcomes are going to lie between those two values, between the mean minus an error of the mean and the mean plus one error of the mean. But what we tend to use is the 2 sigma, or the 2 times the error of the mean confidence interval, which corresponds to a 95% confidence interval, or 95% of the results are going to lie between those 2 values. Again, the mean plus or minus 2 times the error of the mean. So we often quote that 95% confidence interval and compare it to some theoretically accepted value. So if our theoretical value falls within our 95% confidence interval, then the theory and data agree with 95% confidence. And if the theory falls outside of that confidence interval, then we reject the theory with 95% confidence. So that's our quantitative way of determining whether or not our experiment and the theory agree. So in today's experiment, we're going to be constructing confidence intervals for the gravitational acceleration of a ball. So we know that what the accepted value of g is, and we're going to do some trials to get a theoretical value as well. So to do that, you're going to push the ball up into this suction tip. You're going to attach it with this vacuum pump. And then once you hit this little valve, this release valve, it's going to drop onto an ultrasonic sensor that's in the bucket. And what that's going to do is give us a position versus time graph in LoggerPro, and we can fit a parabola to that data. And you want to think for a minute about exactly what section of that data do we want to fit a parabola to, because it's not the entire thing, right? We don't want to be fitting a parabola when it's just sitting here stationary, because we don't expect it to be parabolic motion at that point. It's not until it really starts falling. But the nice thing about the LoggerPro fit, parabolic fit, is that the form of that fit, at squared plus bt plus c, is directly related, it's analogous to the physics equation for the motion of the ball. So you're going to be able to determine the gravitational acceleration of the ball directly from one of those fit constants. So you'll figure that out. And then you'll be asked to do some data analysis on your data. You're going to do multiple trials and construct a 95% confidence interval, see what the accuracy and precision of your data set are quantitatively, how it compares to the theoretical value of the gravitational acceleration, and then repeat that for a couple other data sets. So for the class data set, and then for a few larger ones that we're going to give you. And you're going to be asked to compare the accuracy and precision of each of those data sets and demonstrate that you understand what factors are going into determining which set is more accurate or precise based on sort of what the specifications of the experiment are.